a little while trying to understand some basic elements of rotational mechanics, part of which involved computation of moment of inertia, applying tau equal to I alpha, computing torque, and so on and so forth, and some limitations also. So this basic sheet titled Rotational Basic Spirit is around very direct applications of principles and concepts that we've learned. The whole thing is about getting these basic ideas ensconced. Anything else that you're going to do down the line will only be a combination of these very things. So to be very sure about all of this will, take you a certain distance. So the first problem is about two masses, point masses m1 and m2, and there is an axis perpendicular to the line joining m1 m2 AB, and the first part of this first problem is computing the moment of inertia about this axis AB of the two masses. Very simply, what's the moment of inertia about the axis AB? m1 r1 squared direct plus m2 r2 squared. That's the moment of inertia about the axis AB, right? Okay. The second part of the problem is about finding the moment of inertia about an axis perpendicular to the line joining m1 m2 and passing through m1. So m1 will produce no moment of inertia about this axis, but m2 will produce m2 into r2 plus r1 whole squared, right? So the second part is m2 into r1 plus r2 whole squared. The third part is about moment of inertia of m1 m2 about the line joining the two. What's that going to be? 0. Very clearly 0, because both m1 and m2 are at 0 distances from this line. So the third part is 0. The fourth part is about the center of mass, to find the moment of inertia. So very clearly, how does one find the center of mass? So if this is m1 and this is m2, the center of mass would be located at a distance say this was 0, 0, then this would be 0, r1 plus r2. Yes or no? Right? So the distance of the center of mass from m1 is going to be what? m2 into r1 plus r2 divided by m1 plus m2. Right? That's this distance. And what about this distance? This distance is going to be m1 into r1 plus r2 divided by m1 plus m2. That's this distance. Yes or no? So suppose I call this x1 and I call this x2, then the moment of inertia for about AB is going to be m1 x1 squared plus m2 x2 squared. Yes or no? That's going to be the moment of inertia about the center of mass axis perpendicular to the line joining the two particles. Yes or no? I hope all of you understand how I obtained this position of center of mass from m1. Right? Clear? Stand by. The next problem, again very direct application. 4 point masses m1, m, and m kept at the vertices of a square of side A. I want to find the moment of inertia about an axis perpendicular to this plane and passing through the center of the square. The center of the square would be intersection of the diagonals, right? Very simply, this is A. What would these be? These would be A by root 2, right? A by root 2, etc. Distances of the vertices from the center is going to be A by root 2, A by root 2, right? So then very clearly, each of these would contribute m into A by root 2 whole squared about this axis, right? So 4m into A by root 2 whole squared would be the moment of inertia about an axis passing through C and perpendicular to the plane of the square, Did you get the same thing? Right. Stand by. Third problem is about three particles ABC kept at the vertices of an equilateral triangle of side L, right? And we want to compute moments of inertia of this system of three particles about various axes. Say about the axis AX, right? Now, this is 60 degrees. This is also 60 degrees. This is very clearly 30 degrees, right? This is L. So, about this axis AX, what's the moment of inertia that A contributes? 0. B, ml squared. C, if this is L by 2, isn't it? L cos 30 degrees, L sin 30 degrees. This is L by 2. So m into L by 2 squared. That's the moment of inertia about this axis AX, right? That's the first part of the problem. Second part of the problem is about any side, right? Say about side AB, what would be the moment of inertia? That means if this was the axis of rotation, then very clearly this is L root 3 by 2. The perpendicular distance of C from this is going to be L sine 60 degrees, L root 3 by 2. What's the moment of inertia of A about AB? 0. What's the moment of inertia of B about AB? 0. So 0 plus 0 plus, what's the moment of inertia of M about AB? M into L root 3 by 2 whole square. That's the second part of the problem. The third part of the problem is about moment of inertia about the centroid, perpendicular to this plane, That means M. Very clearly, if you look at the centroid, this length is L root 3 by 2. This is the centroid. What is this? This will be 2/3 of L root 3 by 2. So this length, say this is CAB. What is CG? CG is L root 3 by 2 into 2/3, right? So L by root 3. That means each of these masses, A, B and C, they are at a distance L by root 3 from the centroid. L by root 3 from the centroid. L by root 3, L by root 3, L by root 3. Right? Yes or no? So, about this axis, the moment of inertia contribution of this is going to be m into L by root 3 whole squared, and 3 times that, because each of these would contribute the same. So the third part of the problem is m into L by root 3 whole squared, 3 times this, each of the masses. Yes or no? Right? Very simple. Stand by. A rod AB, uniform rod AB, mass M, length L. And these are 4 axes. There is an axis 1 passing through A and perpendicular to the rod. What would be the moment of inertia about 1? 1/3 ml squared. Yes or no? 1/3 ml squared. Right? Second, about 2. 1/12 ml squared. These are standard results. About 3. About 3, moment of inertia is going to be 0. About 4. md squared. This distance is given to be d. So all mass elements are at the same distance d from the rod. So about this axis 4, it's going to be md squared, where axis 4 is at a distance d from axis 3. As simple as this, right? Stand by. So here we have essentially a rectangular lamina. This is the lamina. Rectangular sheet of side B and length L. Right? And I want to be able to find the moment of inertia about this edge of the rectangle. About this edge of the rectangle. If this is the axis, what's the moment of inertia? That's what I want to find. Right? Very simple. What you do is you take mass elements parallel to this axis AA prime. So this is a mass element. This is a mass element, right? At a distance x, and of thickness dx. And of thickness dx, right? So now, what is this mass equal to? How much is this mass dx, the chosen mass dx? Mass per unit area is m by L into B. What is the area of this? B into dx. B into dx is the area of the shaded region. B units by dx units, right? So B into dx, that's this mass element dm. That's this mass element dm. And all points on this mass element dm are at the same distance x from this axis. So the contribution to moment of inertia made by this dm about this axis is going to be dm into x squared. This is my dm into x squared. Right? The total moment of inertia would be sum of all of this, where x runs from 0 to L. X runs from 0 to L. Very clearly, this is 1/3 ml squared. This is 1/3 ml squared. If I said, what's the moment of inertia? So this was L, this was B. So now tell me, I said if this was my axis, BB prime, this is L by B, L by B, L by B. What would be the moment of inertia about BB prime? 1/3 mb squared. That would be the moment of inertia about this, right? If I said this was my B by L, about an axis passing through the center of mass of this, it will be 1/12 ml squared. It's going to be same kind of calculations. What you do is you take mass elements like this, or you can just apply parallel axis theorem. You can simply apply parallel axis theorem. How do you do that? I about AA prime, which we have computed, is going to be I about this center of mass axis, right? I'm going to apply parallel axis theorem between this axis and this axis. I about the center of mass axis plus m into L by 2 whole squared, right? This distance between the two axes is L by 2. So very clearly ICM is going to be I about AA prime, which is 1/3 ml squared minus 1/4 ml squared, which is 1/12 ml squared. About this. So about this is going to be 1/12 ml squared. But if I said about this, 1/12 mb squared would be the moment of inertia. Clear? Clear? And now tell me, you understand this, right? Can I wipe this off? Have you registered all of this? Right? Now if I said this is a rectangular plate, L by B, right? about this, it turns out to be 1/12 ml squared, right? About this, passing through the center of mass, it turns out to be 1/12 mb squared, right, in the plane. Now tell me, what would be the moment of inertia about this axis? Right, this will be 1/12 ml squared plus b squared, right, about this axis. That means if you choose to rotate the square lamina, rectangular lamina like this, that means if this becomes the axis of rotation, then from perpendicular axis theorem, I about this axis is going to be I about this axis plus I about this axis. So I about this perpendicular axis is going to be what? 1/12 m into L squared plus b squared. Got me? So we have rings, 3 rings. This is a semicircular ring. This is quarter of a ring, mass m, radius r. This is an arc of a ring, mass m, radius r. And I want to find the moment of inertia about an axis perpendicular to the plane and passing through the center of each of these. Very simple. Does it even matter? Does it even matter? If this is just any ring and this is some angle theta, right? I take a mass element here, dm, and about this axis, what is its contribution? Dm into r squared, dm into r squared. And the total moment of inertia would be sum of all of this. Now for all the dm's that you choose along the ring, r is the same, right? So r will come out, r squared, and then we have sum of all the dm's. Sum of all the dm's would be the mass of the ring. So that's simply going to be mass into r squared. So for each of these cases, it's mass into r squared, the moment of inertia. Clear now? Certain about whatever I'm saying? Right? Stand by. These are 2 rods, mass m, length L, and this is an angle, one of the angle bisectors between the 2 rods. I want to find the moment of inertia of the system about this angle bisector A1. Right? That's what I want to do. So first of all, would you want to believe that if I took the other angle bisector A2, then the moment of inertia about A1 will be the same as moment of inertia about A2. That's not going to change. Right. Now, moment of inertia of this rod about an axis perpendicular to the rod and passing through the midpoint, 1/12 ml squared. This also about this axis is going to be 1/12 ml squared. So together this rod plus this rod about this axis is going to be 1/6 ml squared, right? About this axis, the total moment of inertia is going to be 1/12 ml squared into 2, right? 1/6 ml squared. That's 1/6 ml squared. Now, then from perpendicular axis theorem, the total moment of inertia about this must be IA2 plus IA1 from perpendicular axis theorem, right? About this axis is going to be IA2 plus IA1, right? So this must be equal to I about A2 plus I about A1, but I about A2 is the same as I about A1, so this is like twice I about A1. So I about an angle bisector, as you can see, is 1/12 ml squared. Yes or no? Got the same answer? Very good. Stand by. So this is a square A by A. Problem 9 is a square lamina A by A. A by A. And I want to find the moment of inertia about one of the diagonals, say 2. I want to find the moment of inertia about one of the diagonals 2, right? Now one thing, the diagonals 2 and 4 are perpendicular to each other. Diagonals 2 and 4 are perpendicular to each other. Again, because of symmetry, can I say moment of inertia about the diagonal 2 is the same as moment of inertia about the diagonal 4? Right? Right? And what we have seen a little while ago in a rectangular lamina is, so if this was B by L, a rectangular lamina, and this was its center of mass, then the moment of inertia about an axis passing through the center of mass and perpendicular to the plane was what? 1/12 m L squared plus B squared, right? About this axis, right? So that was 1/12 m L squared plus B squared. Now if this was a square A by A, then B will be equal to L equal to A. If this was a square A by A, then the moment of inertia about this axis is going to be 1/12 m 2A squared, which is MA squared by 6. Yes or no? About this axis, 1/12 m A squared plus A squared, right? About this axis. So, good. And can I say I about this axis? These two diagonals are perpendicular to each other in a square, right? So, moment of from perpendicular axis theorem, can I say I2 plus I4, right? I about this plus I about this is going to be I about this perpendicular axis, right? Which is MA squared by 6. But I2 is equal to I4. So 2I2 is MA squared by 6, or I2 is MA squared by 12. So about each of the diagonals is going to be 1/12 MA squared. Got the same answer, right? Stand by. So the 10th problem is about an irregular shaped object, and there are these two parallel axes, axis 1 and axis 2, and it's given that the moment of inertia of this irregular body about this axis is I1 and about this axis is I2, and these two axes are at a distance A and B from the center of mass. That means now if I look at a center of mass axis parallel to the two, then one axis would be A units from the parallel center of mass axis, the other one would be B units from the parallel center of mass axis. I want to connect I1 and I2. Now suppose this was the center of mass axis parallel to the two, then the moment of inertia about this is going to be ICM. So can I say I1 from parallel axis theorem is going to be ICM plus MA squared, right? Similarly, can I say from parallel axis theorem I2 equal to ICM plus MB squared? I subtract the two, I1 minus I2. I1 minus I2 is MA squared minus B squared. That's the relationship between I1 and I2. That's a relationship between I1 and I2. Stand by. So the next one is about a solid cylinder, mass m, radius r, and we look at an axis that lies along the surface of the cylinder parallel to its axis of symmetry, and we want to find moment of inertia about AA prime. We know moment of inertia about this axis is half mr squared. So from parallel axis theorem, I about AA prime is going to be what? Half mr squared plus mr squared, isn't it? Distance between the two axes. So that's going to be 3 by 2 mr squared. Stand by. So this time we have a semicircular disc, uniform semicircular disc, mass m, radius r. क्या निकालना है? Moment of inertia about an axis passing through the center and perpendicular to the plane. About the center of mass? Okay, okay. About the center of mass. Chalo. About the center of mass. I want to find the moment of inertia about the center of mass of this semicircular disc, right? So first of all, do I know the distance of center of mass from O? How much is it? 4r by 3 pi. For a uniform semicircular disc, the distance of center of mass from the center is 4r by 3 pi, right? Now, very clearly, I about this axis, this is passing through O and perpendicular to the plane, and this is another axis, I passing through the center of mass and perpendicular to the plane. So this is I about O coming out of the plane of the board. Say I about O, can I say, is the same as I about Cm plus m into 4r by 3 pi whole square. Can I say this? So now to find I about Cm, I should know I about O, right? How do I find I about O for a semicircular disc? Why? Okay, so right. So this is a half disc. Now mentally imagine a full disc. Mentally imagine a full disc. Now there are two parts of the disc. This is now a total disc of mass 2m. This is a total disc of mass 2m and radius r, right? And the upper disc makes a contribution I about this, and the lower one will also make the same contribution I about this axis. Yes or no? Because of symmetry considerations about this axis. So the total moment of inertia about O perpendicular to the plane is going to be 2I, where I is the contribution made by each of the semicircular portions. Yes or no? So the total is going to be 2I. That must be the moment of inertia of a mass 2m, a full disk of mass 2m and radius r. And a full disk of mass 2m and radius r has moment of inertia about this axis as half of 2m into r squared. Yes or no? So very clearly I is half mr squared, which is I about O also, which is I about O also, right? So this I about O I know. I about O I know is half mr squared for the semicircular portion minus m into 4r by 3 pi whole squared. That must be I about the center of mass. Yes or no? Stand by. So problem 13 is about two rods, mass m, length L, mass m, length L, joined at this point. For this combination, I want to find the moment of inertia about an axis passing through P, this end, and perpendicular to the plane of the L. Perpendicular to the plane of the L. This is what I want to be able to do. You know what I'm saying? Okay. So, first of all, let me call this rod 1 and let me call this rod 2. What is the moment of inertia contribution of rod 1 about P perpendicular to the plane? 1/3 ml squared, right? So, rod 1 makes a contribution 1/3 ml squared about this axis, right? Now, rod 2. Look at rod 2. This is the center of mass of rod 2, right? Now, do I have moment of inertia about the center of mass and perpendicular to the rod 2? What is it? 1/12 ml square, right? About this axis, I know for this rod 2, I of rod 2 about its center of mass, is going to be 1/12 ml square. Yes or no? Now, what is this? So, I know I about this. I want to find I about this for rod 2. What am I going to do? Parallel axis theorem. Achha, this length is L. This length is L by 2. So, L squared plus L squared by 4. 5L squared by 4. So, this is root 5 L by 2 is this length. Using Pythagoras theorem, this length is root 5 L by 2. So, then moment of inertia contribution by 2 at P from parallel axis theorem is going to be, this is 1/12 ml squared, right? Plus m into root 5 L by 2 whole square. And all that you need to do is, you need to add I1P plus I2P. So, the answer is going to be I1P plus I2P is going to be the total moment of inertia about an axis passing through P and perpendicular to the plane. Right? Next problem is about a sheet of radius r, a uniform sheet of radius r, and from which a smaller circular sheet of radius r by 3 is scooped out, leaving you with this portion. And the portion remaining after scooping this out has mass m. I want to find the moment of inertia of this mass, remaining mass m, about the original geometrical center, This is what I want to be able to do, right? Yes or no? Now, one thing. When you look at this whole thing, full sheet, when you look at this full sheet, and you look at the moment of inertia about O, right? Moment of inertia about O of the full sheet, when nothing was cut, was because of two things. Was because of moment of inertia of this smaller disk about O, plus moment of inertia of the shaded region about O, plus moment of inertia of this shaded region about O. Yes or no? Can I say this? And what are we trying to find? We are trying to find the moment of inertia of the shaded region about O. Right? Now, see, the mass of this remaining portion is m. What's the area of this remaining portion? M by pi r squared minus r squared by 9 is the area of the remaining portion. Right? Pi r squared minus pi r squared by 9. Right? So, mass per unit area Whether I obtain from this or I obtain from this or I obtain from the whole thing will remain the same because it's a uniform disk. That's a mass per unit area, right? So which is like 9m by 8 pi r square is the mass per unit area of this entire region, right? So what was the mass of the full sheet? Is mass per unit area 9m by 8 pi r squared into pi r squared into pi r squared was the mass of the full sheet, right? So that makes it 9m by 8. 9m by 8 is the mass of this, right? Now, so I of the full sheet about O is going to be what? Half of its mass into square of the radius. I of the full sheet about O is going to be what? Is going to be half of the mass of the full sheet, which is this 9m by 8 into r squared, right? Now, what is the mass of the smaller sheet? Mass of the removed portion, mass of the removed portion is going to be what? Is going to be 9m by 8 pi r squared into pi r squared by 9, right? Into the area of this is pi r squared by 9. So that makes it m by 8. That makes it m by 8 is the mass of this portion, right? The mass of this portion is m by 8. Now, now for this portion, what's the moment of inertia of this portion about O1? Half of m by 8 into r squared, r by 3 whole squared. So mass of the removed portion, so moment of inertia of the removed portion, moment of inertia of the removed portion, this is the removed portion, about its own center is going to be what? Half of its mass m by 8 into square of the radius, r by 3 is the radius of this, right? Into square of the radius, r by 3 whole square. Now, what is the moment of inertia of this about O? Moment of inertia of the removed portion about O, smaller, that means removed means this smaller disk about O. Smaller disk is removed. About O is going to be what? From parallel axis theorem, this moment of inertia plus, what is this distance? R minus r by 3. This is 2r by 3. Distance between the center of mass axis and O is going to be 2r by 3. Do you understand that? This length is r by 3. This is r. So OO1, as you can see, is r minus r by 3. That is 2r by 3. Right? So moment of inertia of the removed portion about O1 we know is this. So about O is going to be what? Half of m by 8 into r by 3 whole squared. R by 3 whole squared plus mass of this, which is m by 8 into 2r by 3 whole squared, right? So I know this I of the small disk means removed portion about O, I know. This we have computed, so we can compute I of the shaded region about O. Yes or no? Clear? So there is a particle that falls from a point P along the line x equal to x naught. Vertical direction belongs to gravity, right? T seconds later it arrives at Q. I want to find the torque of all the forces acting on the particle about the origin of coordinates. Very simple, yeah. Do you realize that This is the line of action of the force, and its perpendicular distance from O is x naught. So its torque is going to be mg into x naught, isn't it? Line of action of the force into perpendicular distance from O, that will be the torque, mg into x naught. And do you realize it's clockwise? It's clockwise, you know. So if the force is, imagine this to be a rod hinged at O, if this is a force acts, then this rod would swivel clockwise. So torque about O is going to be clockwise. So mg into x naught, which is clockwise. So it's not varying with time, it's time independent. That's the torque about O. In this case, what's the axis of rotation? Perpendicular to the plane of the board. About, yes, z axis. Perpendicular to the plane of the board would be the torque. And what would be the torque about the y axis? 0. Torque about the y axis is going to be 0. What's going to be the torque about the x axis? 0. Because this mg into x naught is torque about this axis, which has no component in the y direction, no component in the x direction. Yes. In any way, in any case, mg, line of action of mg passes through the x axis. So if I take a point on the x axis, then the torque about this point is going to be 0. So torque about the x axis anyways is going to be 0. Torque about O, this mg into x naught, is about an axis perpendicular to the plane of the board. So it's a clockwise torque, right? Launched with a velocity v naught at an angle theta. I want to find the net torque acting on the particle P about the original point of projection. When it reaches the maximum height, horizontally it covers half the range, isn't it? Range is going to be what? V naught squared sine 2 theta by g is going to be the range. That's the range, right? And mg acts downwards. What's the torque of mg about O? mg into r by 2. mg into r by 2. Is it going to be clockwise or anti-clockwise? Clockwise. Clockwise. mg into r by 2, perpendicular distance of O from the line of action of mg. So that's going to be the torque about O, and it's going to be clockwise. That means in the z direction, where r is this. Clear? So we have a force acting at a point 1 comma 1, 5 root 3 I cap plus 5 j cap, and we want to find the torque about O and the torque about A of this force. Very clearly, this position vector is what? I cap plus j cap, isn't it? Is this position vector? And torque about O is going to be what? R cross F. So you just need to find this cross product, I cap plus j cap cross 5 root 3 I cap plus 5 j cap. Right? Yes or no? Or you could have looked at it like this also. See, this vector very clearly, as you can see, 5 by 5 root 3 is 1 by root 3, so it makes an angle 30 degrees with the horizontal. Right? Tan theta is 5 by 5 root 3. This vector makes an angle 30 degrees with the horizontal. And it has a horizontal component 5 root 3, and it has a vertical component 5. Right? Now, there is torque of 5 root 3 about O. How much is it? 5 root 3 into 1. Right? And do you realize this is a clockwise torque? 5 root 3. This is the line of action of the force. This is the perpendicular distance, which is 1 unit, because this point has coordinates 1 comma 1. So 5 root 3 into 1 clockwise. Yes or no? That's a torque because of this component about O. Now, look at this component. 5 units. It's like this. And its perpendicular distance from O is 1. And this component produces anti-clockwise torque. So which is like minus 5 into 1. So this is the net clockwise torque. This produces clockwise torque about O. This produces anti-clockwise. So that's the net torque about O because of this force. Yes or no? You would get the same result if you do a cross product, because again, you know, I cross I will be 0, I cross j and j cross I will all be k or minus k, right? So the net would be k, which is either clockwise or anti-clockwise. And about A, 5 root 3 produces 5 root 3 into 1 about A. And 5 produces how much torque about A? 0. 0 torque about A. Because its line of action passes through A. So this 5 units produces no torque about A. So the net torque about A is going to be 5 root 3 into 1 clockwise. Clockwise. Yes or no? Plane, and there is a sphere of mass m, radius r, and I want to find the torque about an axis passing through this point of contact and perpendicular to this plane. Of all the forces, what are the two forces acting on this sphere? Right, there is mg, which is like this, and there is normal reaction n like this. Now, do you realize the line of action of the normal reaction passes through P? So what's the torque because of n through P? About P? 0. Because the line of action of n passes through P, it will produce no torque about P. Mg could be resolved as mg cos theta, whose line of action passes through P, and mg sin theta, which is parallel to the plane. Mg cos theta produces no torque about P, and there is torque produced by mg sin theta. What's the torque produced by mg sin theta about P? Mg sin theta, and r is the perpendicular distance of the line of action of mg sin theta. Right, so that's the net torque about P. And is it clockwise or anti-clockwise? Clockwise. Mg sin theta will produce clockwise torque about P. That's the net torque about P. Stand by. Now, so, you know, this is like a conical pendulum. This mass m moving in a circle of radius, let's say r, and length of the pendulum is L, right? I want to find the torque because, so there is tension T in the string and there is mg acting downwards. I want to find the torque of T and mg about O and O prime. That's the first part of the problem. Okay. Now, about O prime, say. What's the torque of mg about O prime? Mg into this length r. R is the radius, which is, this is L sin theta, as you can see, L sin theta, isn't it? This is L, say this is L sine theta, right? So torque of mg about O is going to be mg sine theta, L sine theta, clockwise or anti-clockwise? Anti-clockwise, right? So torque because of mg about O prime is going to be mg into L sine theta, right? Now, because of tension, hey, tension could be resolved as T sine theta, whose line of action passes through O prime, will produce no torque about O prime. And T cos theta produces how much torque? T cos theta into L sine theta, right? So torque because of tension T about O prime is going to be T cos theta into L sine theta. So first of all, you know, this was clockwise, right? Like this. No, this was anti-clockwise, anti-clockwise. And T cos theta, this is T cos theta into L sine theta, clockwise. Clockwise, right? Hey, but what's T cos theta equal to? Mg. T cos theta is mg, isn't it? Right? Net vertical force in this direction. So T cos theta I can write as mg. So mg into L sine theta. And will it be clockwise or anti-clockwise? Clockwise. T cos theta will produce clockwise torque about O prime. So this will be clockwise. Right? So this first part. Okay, now this is about O prime. About O. What's the torque of tension about O? 0. Torque of tension about O is going to be 0 because the line of action of tension will pass through O. Right? What is the torque of mg about O? Right, right. See, one thing. This is the line of action of mg, and its perpendicular distance from O is the same as L sine theta. So mg into L sine theta. The important thing is, see, if this is a force F in general, we can generalize this. And this is a point O in general, right? And this torque produces a certain, this force produces a certain torque about O. Now if you take any line parallel to F passing through O, then the torque about this point or torque about this point or torque about this point will be the same. So do you understand that? So this is parallel to mg. If the torque produced about O prime is mg into L sine theta, torque about this point will also be mg into L sine theta. Torque about this point will also be mg into L sine theta. Torque about this point will also be mg into L sine theta. Do you all understand this? Clear now? Now, so we know the torques because of tension and mg, O and O prime. O prime, 0, because mg is parallel to O prime, it will produce. So torque about O prime because of mg is going to be 0. Why? Because mg is parallel to the axis, right? So it will produce no torque about the axis. Torque because of tension about axis, 0, because see, the line of action of T intersects the axis. So torque because of tension about O prime will also be 0, a concept that we just studied today, right? Right, so refer to this inclined plane, fixed inclined plane making an angle theta with the horizontal. There is a block of mass m, there is a string connected, and there is a pulley that moves here. And at a certain instant of time t equal to 0, the pulley has an angular velocity omega like this as shown. What we want to find out is how far the mass will move up. How far the mass will move up, right? That's what we want to find. Now, simple things first. Let's look at the forces acting. On the mass m, there is mg cos theta, mg sin theta, and there is normal reaction from the plane. And there is tension because of the string. On the pulley, there is tension, force because of the tension acting tangentially like this, right? Now, at time t equal to 0, if you really look at the plane, this mass m and this pulley, at time t equal to 0, this pulley has an angular velocity omega like this, so that it has a tangential velocity v naught equal to r omega. V naught equal to r omega is its tangential velocity, right? As shown rightward and upwards. So this mass m also at time t equal to 0, this is at time t equal to 0, has a velocity v naught equal to r omega like this at this instant of time. Now, what happens? Because of this tension, this has an angular acceleration alpha in the anti-clockwise sense, whereas the pulley is moving in the clockwise sense. So there is angular retardation essentially, right? And this mass m has a downward acceleration a. So if I have to write the equation of motion of this mass, what's the equation of motion of this mass? mg sine theta minus t equal to m into a. That's as far as the mass is concerned. So it has a retardation. It has an initial velocity which is v naught like this, and it has a downward acceleration a which tantamounts to retardation given by this equation, which will cause its upward velocity to keep decreasing, become 0, causing it to reach a maximum distance up the plane. All right? Now, the pulley side of the story, realize that there is tension T producing an anti-clockwise torque T into R, and that must be I into alpha. Now, the tangential, see, this point has an acceleration A, same as the acceleration of the mass, right? That's a string consideration. If the mass m has a downward acceleration A, this point on the pulley, topmost point, will also have an acceleration A. And the relationship between the tangential acceleration and angular acceleration is A equal to R alpha, right? So which means I can replace this alpha by A by R. So T into R is I using these two equations, eliminating alpha, T into R divided T into R is I into alpha, alpha is A by R, right? So that's equation 3, say. So you can call this equation 4. So that gives me like a T equal to I into A by R squared. So this T I can plug in terms of acceleration, mg sine theta minus T is I into A by R squared equal to m into A. Now this gives us the value of retardation of this mass. A then turns out to be mg sine theta divided by m plus I by R squared. That's the retardation of this mass. And therefore, and it has an initial velocity v naught, which is like r omega. Initial velocity r omega upwards. And therefore, and with the acceleration downwards, it's going to retard, and therefore the maximum distance that it traverses up the plane x would be v naught squared by 2a, where v naught is this number and a is given by this expression. That'll give me the maximum distance the mass can move up the plane, right? Fairly simple problem, downright application of basic concepts. See, all along we have dealt with pulleys that were light, in which the rotation of the pulley didn't matter, right? And in those cases, the tension was the same at all points on the pulley. Tension was the same at all points on the pulley. But in situations where pulleys have mass and the pulleys can rotate and they have a moment of inertia, then the tension is not going to be the same on both sides of the pulley. Let us understand why. This tension will not be the same. First of all, let's say, for sure, acceleration of this downwards would be the same as acceleration of this upwards. That's guaranteed, right? Now, let me look at the pulley side of the story. Let me look at this point P on the pulley, for example. This point P has the same acceleration A downwards as this mass M. Yes or no? That means the tangential acceleration is A. Tangential acceleration is A. That means if there is tangential acceleration, there must be angular acceleration alpha of the pulley. There must be angular acceleration alpha of the pulley. A is then R alpha. Relationship between tangential acceleration and angular acceleration is R alpha. A is R alpha. Now, if there is alpha, there must be torque acting on the pulley. How would angular acceleration be produced? The cause of angular acceleration would be torque. Right? Now, torque about the center of mass, because this is hinged at the center. Now, if you look at this pulley, and if the tension was the same on both sides of the pulley, and you still expected the pulley to have an angular acceleration alpha like this, now can that happen? No, because realize this T produces torque which is T into R. This T also produces torque which is T into R. Do you realize the torque produced by this is T into R clockwise? The torque produced by this T is T into R anti-clockwise. They would have cancelled off. There would have been no torque and no alpha, which means tension couldn't have been the same. If you wanted alpha in the pulley, you needed non-zero torque. The only way you could have had non-zero torque is if this tension T1 was different from this tension T2. So here's a case, very contrary to all cases that we've seen earlier, where tension on both sides on the same string would be different on the two sides of the pulley. In all cases earlier, we had the same tension across the string. That was because we looked at negligible mass of the pulley, negligible I, negligible alpha, and so on and so forth. It didn't matter to us. But this time, alpha is pronounced. Mass of the pulley is respectable, right? And therefore, the tension on one side will be different from tension on the other side. Now, which means, this would be T1, this would be T2. Do you all understand why the tension would be different on both sides of the pulley? Because that's the only way it could have had a non-zero angular acceleration. That's the only way it could have had a non-zero angular acceleration. So now, alpha is like this. There is T1 acting on this. What is the equation of motion for this? mg minus T1 is ma. That's the equation of motion for this mass. Right? For this mass, there is T2 acting upwards. There is small mg acting downwards. So T2 minus mg is small m into a upwards. That's for the second mass. Yes or no? As far as the masses are concerned, this far and no further. Now the pulley side of the story. What's the torque acting on the pulley? See, this is anti-clockwise alpha. Net anti-clockwise alpha would be because of net anti-clockwise torque. So T1 into R is a anti-clockwise torque about the center of mass minus T2 into R, which was clockwise. So this is the net anti-clockwise torque. This is the net anti-clockwise torque. समझ में आया? That must be I of the pulley, which is given into angular acceleration alpha. But alpha is what? A by R. Angular acceleration is linear acceleration by R in pure rotation, right? So that gives me T1 minus T2 into R is IA by R. Right? So T1 minus T2 is IA by R squared. me call it 3. 3 is IA by R squared. You want to solve for A, right? So what you can do is you can take T1 from here. From here T1 is mg minus ma. From here T2 is mg plus ma. Plug in T1 and T2 here. T1 as capital Mg minus capital A and T2 as small mg plus ma, and solve for A, right? T1 can be written as capital M into G plus A, G minus A, minus T2 is M into G plus A, right? T2 sourced from here, that must be IA by R squared. And you can solve for A. You can solve for A, the acceleration of the system. Right? So pulleys where you take into account rotation and the mass of the pulley, you will have to look at different tensions on both sides of the pulley. Stand by. Rod, mass M, length L, fixed at edge. This is my hinge, and this therefore will be my axis of rotation, perpendicular to the plane of the board. Now at the initial instant of time, we want to compute the acceleration tangential and radial of the point A. We want to compute the tangential and angular acceleration of the point A. Alright? Okay. First of all, let's have a free body diagram of the rod. Tell me, what are the forces acting on the rod? Okay, so there is a hinge force which will have, let's say, a vertical component N1. There is a hinge force and would have a horizontal component N2. That's one force acting on the rod, right? At the hinge there is going to be a force. What else? Mg. Mg. From the center of mass there is, so this is L by 2. Now, if I have to compute alpha of the rod, how do I compute alpha of the rod? Tau equal to I alpha. Tau about what point? About the hinge. What is the torque because of N1 and N2 about the hinge? 0, because their line of action passed through the hinge. So N1 and N2 will produce no torque about the hinge. What's the torque of Mg about the hinge? Mg into L by 2. Clockwise or anti-clockwise? Clockwise. Clockwise torque. That must be I about the hinge. What's I about the hinge? 1/3 ml squared. Into angular acceleration alpha of the rod. So that gives me alpha equal to 3g by 2l, angular acceleration of the rod. Right? Right? Now, look at the point A. Look at the point A. The point A is moving in a circle of radius L, isn't it? The point A is moving in a circle of radius L, centered at the hinge. Right? With angular acceleration alpha, with angular acceleration alpha. So the tangential acceleration of the end A, would you not want to believe, will be L alpha, R alpha? It's moving in a circle of radius L, centered at H. Tangential acceleration is angular acceleration into the radius of the circle L. So L alpha kya ho jayega? 3g by 2. That's going to be 3g by 2, isn't it? L alpha is 3g by 2. That's the acceleration of the end A, tangential acceleration, right? Now, there is also a story about the radial acceleration of the end A. There is a radial acceleration, AR. This is my tangential acceleration. This is my tangential acceleration. There is a radial acceleration. Why should there be a radial acceleration? If it's moving in a circle of radius L, there must be centripetal acceleration, which is this radial acceleration. This radial acceleration is because of centripetal acceleration. But at this instant of time, it starts from rest. So omega is 0 of the end A. Omega is 0 at this instant of time of the end A. It's starting from rest, right? So what is my radial acceleration? Omega squared L, which is 0 at time t equal to 0. Because omega is 0 at this instant. So radial acceleration is going to be 0. Okay, now tell me at this instant of time, what would n1 and n2 be? What would n2 be? First of all, tell me what would n2 be? What does n2 do? What would n2 do? It will produce centripetal acceleration to the center of mass, right? This is the net force and its impact would be felt on the center of mass. Would provide the center of mass a radial acceleration AR prime. But again, what's the radial acceleration of the center of mass? Center of mass is also moving in a circle of radius L by 2. At this instant of time, its omega is 0. So radial acceleration of the center of mass at this instant is 0. Right? Because omega is 0. And therefore, n2 at this instant will be 0 because n2 would have given it that horizontal acceleration to the center of mass, right? The impact of force is directly felt at the center of mass. So n2 would have given acceleration to the center of mass in this direction. n1 would be impactful for acceleration in the vertical direction. Yes or no? Now, can you tell me what is the acceleration of the center of mass vertically downwards? L by 2 into alpha. It's moving in a circle of radius L by 2. So that's going to be L by 2 into alpha, L alpha by 2. So that will make it 3g by 4. That will make it 3g by 4. That's the vertical axis. What causes vertical acceleration of the center of mass? Net of all vertical forces, mg minus n1. mg minus n1 is m into acceleration of the center of mass in the vertical direction, which is 3 mg by 4. So n1 at this instant of time is mg by 4. And n2 is 0 at this instant. Yes or no? Do you understand this? Confused? So, we want to compute next. So, we have done part 1, part 2 acceleration, radial and tangential we have done. Part 3 hinge force at this instant we have computed. N2 is 0, N1 is mg by 4. Find alpha and omega when the rod becomes vertical. So far so good, right? We want to find alpha and omega when the rod becomes vertical. Have you actually understood everything that I have said here, or are there issues pending? No, no? समझ में आया? Now when the rod becomes vertical, so this was the original rod, hinged here. This was the end A. A moves in a circle of radius L, eventually comes to this point, A prime, right? When the rod becomes vertical, I want to be able to find the alpha of the rod and the angular velocity of the rod. I want to find what the alpha is, and I want to find what the omega is at this instant. Okay. First of all, to find alpha, what would you want to do? Calculate the torque about the hinge. Isn't it? You want to calculate torque about the hinge? Do you realize that what are the forces acting? Mg downwards, and there is hinge force, which has a vertical component and there is a horizontal component. There is a hinge force. What's the torque of the hinge force about the hinge? 0. What's the torque of mg about the hinge? 0. So what's the net torque about the hinge? So what's the alpha about the hinge? 0. So alpha is 0. Yes or no? Clear? Now, mg was originally, let's say, acting through this point, center of mass, and then mg comes down here. Mg falls by what amount? L by 2. There is loss in potential energy of the system. Yes or no? How much of potential energy is lost by the system? Mg into L by 2. Yes or no? Where does it feature? Gain of kinetic energy. So when this comes here and it has acquired an angular velocity omega, this is a rod in a state of pure rotation. This is a rod in a state of pure rotation about the hinge. What's kinetic energy of the rod in this state? Half of I about the hinge into omega squared. That's kinetic energy in pure rotation. I about the axis of rotation into omega squared. That's the kinetic energy in pure rotation. So that must be half of I about the hinge into omega squared. What's I about the hinge? 1/3 ml squared is 1/3 ml squared. So that's half of 1/3 ml squared into omega squared. And that will give you omega when the rod becomes vertical. So when the rod becomes vertical, omega is maximum, but alpha is 0. Right now? Then what else do we have in this? Hinge force when the rod becomes vertical. Hinge force when the rod becomes vertical. So when the rod has become vertical, I want to find the hinge force, N1 and N2. Alpha is 0. Right? Look at the center of mass. It will have tangential acceleration L by 2 alpha. This length is L by 2, R alpha, which is 0. That means N2 must be 0. N2 must be 0, yes or no? Because the net force and net acceleration in this direction of the center of mass is 0, so the net force acting on the system horizontally must be 0. Confused kya? No. Now, in the vertical direction, what is the net force acting upwards on the system? N1 minus mg. And it has an angular velocity omega. So would you not want to believe that this must be m omega squared into L by 2? Look at the center of mass perspective. N1 minus mg provides the center of mass the required centripetal force so that it can continue in a circle of radius L by 2. Omega we have computed, so we can obtain omega we have computed at this instant of time using energy principles. So we can obtain the value of N1.